Okay. Also remember, local min and max is the same thing as relative min and max, right? So make sure you're used to both those vocabs. And then we have absolute min and absolute max. Okay, so number 2. We're going to follow the 5-step process on number 2. What is the domain? It's cubic, right? X cubed. What does an X cubed graph look like? Like an S-looking thing, curvy. So the domain, is that going to be negative infinity to positive infinity? We have a restricted domain that's given to you. Oh. Okay. Alex, how can we say the domain for this one? Okay, 1 to 9. And what goes around the 1 and the 9? Perfect. Yeah. Okay, what's the second step? Find the derivative. And then the third step is look at restricted values, or critical points. Okay, so f prime, or dy dx, equals, okay, Gisu, what's the derivative of this guy? Good. Okay. Part C, find the critical points. Critical points is when the function or the numerator equals 0. What, can I put this over 1 and then the function's just the whole polynomial is just your numerator? And restricted values happen when? The denominator is 0, which makes the function undefined, right? So denominator equals to 0, or the f prime of x is undefined. Okay? So, critical points, we set the numerator, which is just the polynomial, equal to 0. It's a quadratic. Right? Ariel, how do we solve the quadratic knowing when it equals 0? Here, exactly. So, two numbers that multiply to 12 but add to negative 8. Negative 6, negative 2. You gotta be careful with your signs. X minus 6, x minus 2. Any questions? Factoring? 10th grade right there. Okay, so we use the 0 property. You can actually do these ones in your head. But you set each of them equal to 0 separately. And so we have our two critical points are at x equals positive 6 and positive 2. Any questions on finding the critical points? Okay, do we have any places where we'd have undefined? And find the function was undefined, because no. Because this is just quadratic, it just goes forever, there aren't any holes. So there are no restricted values. So we take our critical points, maybe C, D comes after C. What do we do for part D? Make a number line. What function is our number line representing? F prime. And we put 2 and 6. Okay, F prime is a quadratic. Is it a positive quadratic or a negative? It's positive. So, I'm sorry, I've been losing my voice all weekend. How do positive quadratics look? Concave, up or down? Up. So it starts up, and then it goes down, and then it goes up, right? It's going to go like that. And somewhere along the way it crosses the x-axis. So, we can say A, B, C, D, E. This lesson was talking about maxes and mins. Is this going to have, because the original function f of x was a cubic, is it going to have an an absolute max, an absolute min. We would almost say no except for, used to? We have a restricted domain. We're only looking from 1 to 9. So this one's actually going to have an absolute. So not only do we want to know what 2 and 6 create, if they're relative mins or maxes, but we also want to know about the endpoints. So I'm also going to put 1 here and 9 here, right? Because we also need to include the endpoints. So let's start with 2 and 6 first of all. What can you say about x equals 2? Goes positive to negative. What type of max? Relative. At least we think. We'll have to check the endpoints in just a sec. Relative max. Okay, what about 6? It goes from decreasing to increasing. So that would be relative min. Okay. If we think it's relative, we have to check the endpoints 1 and 9 to make sure those are higher or lower. How do we check 1? We plug into what? The original. So let's see. F of 1, 1/3 times 1 cubed minus 4 times 1 squared plus 12 times 1 plus 5. Okay, so 1's really nice. 1/3 minus 4 plus 12 plus 5. And we'll need to plug in 9 as well. Okay, can you get both of those for me? Okay. So, what did you get for f of 1? Still working on it? Maybe we'll grab this off the printer really quick. Okay, f of 1 and f of 9, and decide what's your relative max, your relative min, your absolute max, your absolute min. Who has f of 1? (13 1/3). Does someone second that? Okay. .3 repeating. Okay, what about f of 9? Okay. Okay, let's also, when we write our sentences, we do need to know f of 2 and f of 6. So find both of those. Determine if they are actually an absolute max or if it's just a relative max or relative min. Okay, does anyone have f of 2? Is that rounded? I have 15 and 2/3. So 15.6 repeating. That's f of 6. Yeah, agreed. Okay. So, f of 2 is 15.6. F of 9 is 32. So does that mean f of 9 is the absolute max? Because it goes all the way up to 32. Is f of 9 going to be the absolute max? What? Actually. Look at the interval, our interval for our domain. It doesn't include 9. Oh. On 1, do we include 1? Yes. So, no, you just don't. You just don't say that that's an absolute max. Okay, so for our, we can say we have a relative, right? F of x has a relative or local, they're interchangeable, relative max of what? What's the height? Of nope. We're going for this one. This is the relative. Of 15.6 repeating, or did you have the fraction 47/3? 15 point, let's do 4 decimal places though. You can either put a bar over it, or you can leave it as the fraction 47/3. At of 15.6 repeating, at x equals, what was the x value? 2, and you have to explain why you know it. Because f prime of x changes from positive to negative. Okay? Right, let's look at our minimums. Do we have an absolute minimum? What's our absolute minimum? Yeah, it's this one right here, right? So f of x, and actually our absolute minimum, is that an endpoint? Nope. Absolute minimum was actually in the middle of our interval. That's why you need to check your endpoints and see. Sometimes the endpoints are them, sometimes they're not. F of x has an absolute, you have to say absolute, minimum of what? Of 5 at x equals what? 6. So we'll practice saying this phrase over and over and over. Because, how can you prove that you know that? Changes from negative to positive. And how can you prove that it's not just a relative? How can you say, no, that's not just a relative minimum? f of 6, is that greater or less than f of 1? This one. It's less than. So we need to not just prove that it's a minimum, we need to prove that's the absolute by saying, and because f of 6 equaling 5 is less than f of 1, which equals 13.3333. We're practicing 4 decimal places. So if it's absolute, make sure you prove that it is the lowest or the absolute min or max compared to relative. And the last one, f of x has a, which one am I missing? Okay, Reed, what do we call this one? So when f equals 1, is that going to be a maximum or a minimum? And is it relative or is it an absolute? Relative minimum, because it starts increasing. On the right-hand side, it's lower and then it increases. And we know it's relative because this guy is lower, which is the absolute. So this is a relative min. So f of x has a relative, or you can say local, minimum. What do we say after the word minimum? Of its height. And it was 13.3333 at x equals 1. And we know this because, does it change from negative to positive? No, it's an endpoint. We don't have anything on the left-hand side. So we'd say because f prime of x is positive after the endpoint. F prime of x is positive after the endpoint. Okay, I don't have a lot. So I think we did number 3, correct? Let's try another one, number 4. Is anyone still writing this? I'm sorry, I flipped it. Does anyone still need this? All right, number 4. What's the domain? Ooh. Square root functions. I like to visualize what does a square root function actually look like. So it's marked like this of some form. Does it go negative infinity to positive infinity and just the parent function? No, there has to be a starting point somewhere. Okay, so you need to find what is the smallest number with square roots. We can't take negative square roots. Can you take a square root of 0? Yeah, so you want to know, when does this inside equal 0? Plus and minus 2. Yep. So, equals plus and minus 2. What does that mean for our domain? Like that. Oh, in brackets. So you're saying anything between those would work? If I plug in positive 1, can I just take the square root of it? Square root of 4 minus 1 is 3. Can I take the square root of a positive 3? Well, if I plug in negative 1 or 0, Would they all work? Because you're squaring them. But what if I plugged in -3? No, because then you plug in -3, which is outside what you gave me. -3 squared is 9. 4 minus 9 is -5. Okay, so from -2 to +2 would work. Okay, and then we find g prime of x. For this one, taking the square root function, I think it's easier to look at 4 minus x squared, all raised to the 1/2 power. Yeah, our friend the chain rule. Okay, so will you take the derivative? Remember, chain rule at the end means you have to multiply by the inside's derivative. Multiply by the inside's derivative. Oh, my paper's actually different. Okay, Hawa, what'd you get for the derivative? I think you're really close. You forgot one detail. I want you to forget. Yeah. And this minus 2x is the derivative of the inside, right? Good. Now what? Good. Critical points and restricted values. Okay, so critical points we're looking for when the numerator equals 0. And we say numerator because you can, if it's equal to 0, the denominator would cancel away, right? Because you can multiply the denominator over to 0 and then it would just disappear. Restricted values is when the denominator equals 0. Well, do we have numerators and denominators in this derivative? Yeah. G prime of x equals, let's see. Actually, we can even cancel negative x over 4 minus x squared to the positive 1/2 if we move it down to the bottom. So we do have numerators and denominators. Okay, so go find the critical points and restricted values. The critical point is the easy part. Restricted value takes a little more work. Is this the same thing for the denominator? Is this really the square root of 4 minus x squared? Does that equal 0? So if you're thrown off by the 1/2 exponent, it just means the square root. So how do you undo a square root? Square everything. Okay, Joanna, what'd you get for critical points? Yeah, right, because negative x can equal 0, so x can equal 0. And the denominator, if we square both sides, 4 minus x squared equals 0. This looks familiar. Plus or minus 2. So we'll get undefined plus or minus 2, so those would be restricted values. Now what do? Do our famous number line. And this is for G prime. Make sure you're labeling. Make sure you know what the number line represents. It represents the derivative. We put -2, 0, and +2 on the number line. Now this function's a little intense. How can we figure out if it's increasing or decreasing? Yeah, plug in values. I think starting with 1 and -1 would be the easiest one. And we're plugging into G prime. So if you plug in a +1, find G prime of 1, that's not too bad, and G prime of -1. Find both of those and determine, are we getting positive numbers or negative numbers. Okay, when you plug in +1, did you get a positive or a negative value? Negative. I got -0.6, essentially 0.577, right? Okay, when you plug in -1, yep, I got positive 0.577. So we have a negative and a positive. What are some numbers we can try on the left and the right ends? Why not? If we tried a -3, let's just try it. See what would happen. If you plug in -3, you get error, non-real. Okay, because our domain is restricted to -2 and +2. So this is imaginary. Okay. So I want you to go through on part E now and write down all of your relative max, mins, absolute max, or mins if there are any. Always remember to check your endpoints too. Right, your maxes and mins can be your critical points, restricted points. It can also be your endpoints. So make sure you always check your endpoints. They'd both be relative maxes. The -2 and +2 come out the same. Yeah, so I'll have to see. Where's my calculator? Ooh. Except for... When you plug in -2 and +2, has anyone done that? It is the square root of 0, but where's the square root at? Oh, I was plugging into the derivative. Sorry. I was like, division by 0. I was plugging into the derivative, but that's wrong. 4 minus... Yeah, it would just, both those are square root of zeros. Okay, this one I have on here is a different problem. Okay, so what does 0 become? Is that a relative max or a relative min? When you plug in 0, it becomes square root of 4, which is... Square root of 4 is plus and minus 2. Let's look at the graph. Let's just graph the function. Go to y equals and graph Square root, make sure you do parentheses, 4 minus x squared. Look what happens. At x equals 0, okay. That's crazy. I don't know how they did that. I'm going to clear it out. Some genius spends more time filing the calculator than using their brain to do their math homework. That is pretty cool, though. I'm going to erase it, though. Okay. Invalid dimension. Look at your window. Yeah, I don't know how they did that. I'm going to erase it. Are you good with that? Reset. Okay. Unfortunately, the face is gone now. Let me see yours. Oh, you have your plots on. Let's take those off. That works. Your plots are just on. Okay. So, do we end up getting positive and negative 2? Does it create a circle? That's the question. Is it creating a circle? No. Okay, so this is just a negative. If you're decreasing, that should be a minimum, not a max. Aren't you guys showing a maximum in your graph? Except for we're not applying. Oh gosh. Are they? Oh yes. Because our positive 1 is here. So that was the negative, and the negative 1. Ah, there we go. Yep. Because it's supposed to be max. Now that matches our graph. Okay. I did the positive g prime of 1 first. So that's supposed to be negative. I put the minus sign on the wrong side. And then the fg prime of negative 1 is positive. Okay, so we have at negative 2 and positive 2, we plug those in and we got errors, right? Right here, because, oh yeah, we have imaginaries on those sides. Okay, so what would you say the 0 is? Let's say it's an absolute. So f prime of x, not f prime, regular f. Oh, thank you. Goodness gracious. G of x has an absolute max of, let's do of first. We plugged in 0 and we got what? 2. Of 2 at x equals 0. Because, how can we prove we know this? What is it, Alex? Yep, goes from positive to negative. And to show it's absolute, we'd also probably want to say, and because the other guys, g of plus and minus 2 both equal what? The what? Yeah. And because plus and minus g of plus and minus 2 equals 0, which is less than g of 0. Oh, I would explain all of these things. You can say all of this stuff by EVT. You have to be very specific. Okay, I think that does it for, that's the first derivative test. So g of x has an absolute min at -2 and +2. Okay, write that in. Let me pass out the second derivative test. What? No, we just did this is called the first derivative test, testing for when we have maxes and mins, and now we're going to continue on to the second derivative test. Even though it has the word test in it, doesn't mean we're actually taking a test right now. Did everyone get the worksheet for the homework last time? DC, did you get that with the sub and Mr. whatever his name is, Mr. Sharp's class? Everyone else got their worksheet that you were supposed to do your homework on? Okay. Let me pull this one out. 5.3. Yeah, we actually did that when we did the extreme value theorem. It is right here. Okay, so first derivative test is what we've just been doing. What did we find with the first derivative test? Yeah, we found when we could get relative mins and maxes and absolute mins and maxes. It also told us intervals of increasing and decreasing. Okay, so once this comes up, I'll write that in. Okay. So first derivative tells us relative and absolute maximums and minimums. And we were also able to find the intervals of increasing and decreasing. Increasing / decreasing intervals. By finding those critical points, restricted values, and yeah, if the derivative was positive, that would be an area where it was increasing. If the derivative was negative, that would be a part where the function was decreasing. Okay? Second derivative is new. Second derivative will help us find where we have concavity. We're not going to get cavities like in your teeth. But concave up, I've said these words, this phrase a few times. Concave up, what does that look like? Yeah, like a U pointing up. Concave up looks like that. Versus concave down will look like the flip, right? Going down. Second derivative can also find what's called the point of inflection. The point of inflection is where we change from being concave up to concave down, the point where it changes concavity. And points of inflection. Sometimes you see it as POI. P and I capitalized because those are the important words. O not so capitalized. Okay, and that tells us where the original function changes concavity. Okay, a good example of this would be like the x cubed function. Do you see any concavity on that? Yeah, there's actually from here to here, it's essentially concave down. From here, oops, I guess that's actually the other one. Here to here, it's essentially concave up. And right here would be called point of inflection. Okay, that's where it's changing concavity because it was kind of curving down. Now, and then it starts curving up. Okay, so that's what I mean by point of inflection, where the curve kind of changes direction. Okay, so if I give you a function, f of x, that looks like this. Let's see, we have -2 right there, and this goes out to 6. Ooh, to 6, I might need to make that a little smaller. 1, 2, 3, 4, 5, 6. Here's -2, here's 5. Okay, you have an intersection at -2, an intersection at 0, an intersection at 6. Okay, we have a minimum at -1 and a maximum at 3. And I don't really, for these purposes, don't really care about those heights of minimums and maximums. Okay, what could you tell me we would see on the derivatives graph? Okay, so I don't think it's increasing before negative. Yeah, so here we're decreasing. Decreasing. Here it's still decreasing. Then what happens? Then we start increasing, and then what happens? After the max, it starts decreasing. Okay, when the function is decreasing, the derivative is negative. So until -2, we should be negative. 5, 6. What happens at -2? Actually, what happens at -1? At the minimum. What's the tangent line right here? 0. So a tangent line of 0, the derivative has a 0, meaning an x-intercept. Okay, is there another instance where we have a tangent line of 0, or we have another x-intercept? Yeah, at 3 we have a tangent line of 0, so at 3 the derivative has an x-intercept. When is the tangent line the steepest? Here it is 0, and then it goes like this, and then it goes to 0. When is the tangent line the steepest? The point of inflection, which is approximately right there. the point of inflection, the tangent line is the steepest. So what do you think that creates on the derivative? So here we are negative because it was decreasing until negative 1. And then after negative 1 it becomes positive because it was increasing. And it's, then let's see, line at 3. Yep, it's still positive until 3. And after 3, x equals 3, it starts decreasing, which is negative. Does that make sense? I like to start with the tangent line equaling 0. For me, I like to find the x-intercepts first, because now we're going to do the second derivative. So is there any place where we have a tangent line of 0 has a slope of 0? Yeah, 1, 2, 3, 4, 5, 6. So at 1, we have a nice slope of 0. Okay. Until that point, what's going on with the function? It's increasing. So our graph would be positive. Yep, it's linear. Okay, because this is increasing, and then it starts decreasing, which makes the derivative of that negative. Okay. And notice where the point of inflection was. From the original function, you said this was point of inflection. What does it become on the second derivative? On the second derivative, it becomes the 0. Point of inflection is when f of x, and I guess we'll do f double prime of x, equals 0. Okay? So, let's write some information we've just learned. About f, we knew we had a max. About where? X equals on f. X equals 3. We have a min where? X equals negative 1. This is all about f, the original function. Okay, then we have intervals of increasing and intervals of decreasing. Okay, Ethan, what would the interval of increasing of f be? Good, and what goes around the negative 1 and 3? So at negative 1, is it increasing or is it changing from decreasing to increasing? It's changing, so we would use parentheses because it's in the process of changing from increasing to decreasing. Okay, interval of decreasing. Claudia, can you tell me the interval of decreasing? From the original function, where is this function decreasing? So you can look at 2 places. It's decreasing from there to there, from here to here. You can also look at the derivative because it's when the derivative is negative. Okay, so I should hear 2 intervals. So from here to here, what are those x values? Which is the same as from here to here. What are those x values? What does this arrow mean? Negative infinity, so it has to be a parenthesis, 2. Negative, yeah, it is 1. Union, because there's another one, right? When does it start decreasing again? 3, 2. But this arrow means it goes on forever to infinity. Okay? We also can see some concavity. It's concave up. You've already found your point of inflection. From negative infinity until we get to x equals 1. And then it changes concavity. It becomes concave down from 1 to positive infinity. Normally you'll have the polynomial, so you can actually just take the second derivative and it tells you the exact value. This was a little bit of eyeballing. Okay. And then that point of inflection happened at x equals 1. Okay. So the next example actually gives us a polynomial. So if you flip it over to number 1, take that information, we go through the same 5-step process, but we have a lot to answer. We have increasing and decreasing intervals, maxes and mins, and concavity. Okay, so example 1, what is the domain of this cubic function? All real numbers. You can say all real numbers, or you can do negative infinity and positive infinity. You might want to write small in this, by the way. There's a lot to answer. Okay, John, what's our second step? Good. So, John, dy dx equals what? Good. Okay, polynomials are really nice to take derivatives of. And it actually makes step C nice, too, because we don't have a fraction. So for critical points, we're looking when the numerator equals 0, restricted value, the denominator equals 0. Is that ever going to happen with this polynomial? So there are no restricted values, but critical points, are there some critical points? 0 equals 12x squared minus 24x. What did you solve for critical points, Amisha? Yeah, what factors out of those two? Oops, what? Sorry, I just hit some weird button. 12, I think something else as well. 12x. Giving us x minus 2. Yeah, there are two critical points. Don't forget to set 12x equal to 0 and x minus 2 equal to 0. So we get two critical points. X equals 0 and positive 2. Okay, Jake, now what do we do? For which function? dy dx. So what do I put on the number line, Jake? 0 and 2. This is one of those nice functions because it's an x squared. Is it a positive x squared or a negative x squared? Positive, so it should go, our graph essentially looks like this. So it's positive, negative, positive. Okay. So just from doing this is the first derivative test. What can we say off of the first derivative test? Okay, we're having a max and a min. We can also say intervals of increasing and decreasing. Okay. So if we were to say, where is it increasing? Y is increasing. That's positive. Okay, negative infinity to 0, we use a parenthesis. Union, Claudia, when else is it increasing? To Infinity, good. Why do we know this? Because y prime of x, yeah, is positive or greater than 0. So make sure you explain why you know it. Y is decreasing. Rebecca, when is y decreasing? And what should I put around the 0 and the 2? Good. Why do we know this, Rebecca? Yep, y prime of x is negative or less than 0. Okay? And let's do the mins and maxes here. Is there going to be an absolute min or max, knowing that this is a cubic function that goes like this? Is there going to be an absolute? No, it goes up and down forever. Okay, so we do need to plug in these two values. You need to plug in f of 0 and f of 2 for when you're answering if it's relative min and max. Okay, so this one we already know is a max. F of x has a relative, because we know the function goes up forever, max of, what do you get when you plug in 0? 0. Of 0 at x equals 0. And we have to say this because why do we know this is a relative max? Right. Because dy dx changes, yeah, why? Changes from positive to negative. Okay, and we have a minimum. We know it's a relative min because the cubic goes on forever because of the domain. Y has a relative min of something. You have to plug in 2. Negative, I have 32 and 48, yep, negative 16. Of negative 16 at where? X equals 2, because dy dx changes from, how do we know this? Negative to positive. Okay, that's all first derivative test. Now it's time for second derivative, which just means we come back up and we redo the b step. Step b again. Now, second derivative looks like this. Either you can put y double prime or d squared y over dx squared. That's where the squares go. The first one goes with the d. The second one goes on the x. What's the second derivative, Joanna? If this is the first derivative, what's the second derivative? Good. And this function will become nicer for us. Each time we take the derivative of a polynomial, it gets nicer. So part C, critical points, is when this function equals 0. What is it, Alex? At x equals 1. Are there any restricted values? No, because there's no denominator. It's just a nice linear function. None. Okay, so part D, we draw a number line, labeling it as our second derivative. And we put a 1. This is nice and linear. So is it positive negative or negative positive? This is a positive linear, so it goes like this, right? It goes negative to positive. Okay, then you have to tell intervals of increasing and decreasing, relative maxes and mins. It's actually, excuse me, we don't do that on this one. This now tells us the point of inflection and concavity. Okay, can you tell me the point of inflection? And the point would be 1 comma, you plug in 1 to the original function, we get 4 minus 12, negative 8. So we have a, y has a point of inflection at 1, negative 8, because y double prime, or the second derivative, changes signs. And with that sign change, we can see the concavity. When it's negative, do you think that's a concave up or concave down? From negative infinity to 1, it's negative. Is that concave up or concave down? It's down. Yep, so this guy here will be concave down, and this will be concave up. So you just need to write that in. Okay, so y is concave down on the interval negative infinity, that's not an infinity, that's an 8. Negative infinity to 1. We know this because y double prime is less than 0 or negative. Or you can say d squared y over dx squared. And the last one, y is concave up from 1 to infinity, because y double prime is positive. That's the second derivative test. So the steps are the same, you just apply them to the first derivative, and it tells you concavity and points of inflection. Okay, your homework on this one is really short, and then you have this first derivative test worksheet, because you're doing 1, 2, 3, 4, 5, 6, 7, 8. Just 10 problems in this worksheet. Okay, next time we'll answer it if you still have questions on 5.1, was it 5.1? If you still have questions on 5.1, I'll take questions on 5.1. Okay? And if you have questions on this one, I'll take questions on this one, both next time. 5. We're just doing these tonight. Oh, it's not letting me write. There we go. Okay. Yeah. I'll look and see if I have any. So next time, let me write this down first and then look and see if I have. Oh, there are 2. Oh, I see what you're saying. Okay, I thought you were just talking about that chart thing. Yeah, because we've done all of 5.3. We'll take questions on 5.1 and questions on 5.3 next time. Okay, so the pink things, I don't know if I have extras. Oh, look. Oh, I see pink. Oh, that's not the right pink, though. Okay, I'll print them off. Who needs another copy of the homework set? Thanks. The printer's kind of slow. Well, you have a few minutes, so let's start working on the worksheet. Grab those off the print.